So we're going to connect those dots in a piecewise linear fashion. Now let me ask a question. That turns out these piecewise linear, this piecewise linear curve is not smooth. Suppose instead we were doing everything in 1 year intervals because we had 1 year growth rates. Suppose we had been projecting, doing this calculation for the average growth rate, and instead of using annual growth, we had been calculating it every 6 months, so every half year. So originally what we had was P of t equals P0, 1 plus R bar. You know what? I'm getting tired of writing R bar. For the moment, I'm just going to write down, I'm going to forget the bar. We're going to talk about the average growth rate. So this is what I'm going to do. If I say R 2020, then you know that I'm talking about the growth rate in a particular year. If I just write down R, then I'm going to be talking about the average growth rate over a period. So if I have a subscript that indicates the year, then this is going to be an annual growth rate. If I omit the subscript, that's going to be the average growth rate. So I'm going to say PT equals P0, 1 plus R, that's the average growth rate, to the T. Suppose we did this whole thing again for 6-month periods rather than 1 year periods. Then very approximately, it's going to be that the population in the year T is going to be almost 1 plus, now if it was half a year, then there are 2 half-year periods per year, so that growth rate would be approximately 1/2 the size, and we would do it twice as many time periods. So to get from 2021 from 2000, we use 21 terms. If we were doing it in half-year periods, we would have twice 21. We'd have 42 periods, and the growth rate over each 6-month period would be roughly half. We could do, instead of twice a year, we could do it every month. So there'd be 12 months, and so the population at time t would be, I'm sorry, did I switch from here someplace? I need to make that a kt. I need to make that a k0. This has to be a kt. This has to be a k0. And I did the same thing here. So this has to be kt, k0, kt, k0, kt equals k0. And if I was doing this by monthly periods, then there'd be roughly that annual growth rate would be cut by 12, and there would be 12t. There's actually no reason why I couldn't do this in daily periods. So that'd be kt times k0, 1 plus r over 365. And now I've got lots and lots. So over 20 years I have, do I do that right? Yeah, I have 7,000 of those things, 7,300 of those things, t. I could do this every hour. I could do this every minute. I could do this every second. And if we do that thing, what we'd be calculating would be what's called the instantaneous growth rate, R. So now what we're doing is we're asking what is the limit as n goes to infinity of 1 plus r over n times nt? Well, it turns out that Jacob Bernoulli worked on this problem at the end of the 17th century in 1690. He looked at this problem. It turns out that this problem is very closely related to, there's a slightly easier problem, that is the limit as n goes to infinity of 1 plus 1 over n to the nt. And you may not be surprised about this, that this thing, Bernoulli demonstrated that this thing has as its limit e to the t. That's e is the basis of the natural logs. So that's the transcendental number 2.71828, so on. That's Euler's number. So the limit of this 1 plus 1 over nt is e to the t. And it turns out that in our original question, the limit as n goes to infinity of 1 plus r over n to the nt, that goes to e to the rt. So this thing describes a model of growth where we said that kt equals k0 e to the rt. There is our 1 plus r over some number times that some number times t. If I was going to smaller and smaller and smaller time periods, then we approach e to the rt. This thing, I'm going to draw a box around that, and I'm going to draw a box around that in red, and that is kt equals k0 e to the rt. This thing is called exponential growth model. And by the way that we constructed this thing, you can see that it is incredibly close to kt equals k0, 1 plus r to the t. This is our geometric growth model. That's our multiplicative model. They're very closely related. And you can see why they were closely related. It's because we took that geometric model, and then as we got smaller and smaller time periods, then we ended up with this model. What's going to happen is that when we do that, then we have all these 365 in each of these years. Each day, we're actually going to do it by every hour, every minute, and then it turns out that this is going to be very, very, very smooth. So as we get smaller and smaller time periods, this curve becomes smoother and smoother and smoother. There's a similarity in the structure, the way I've written this thing down. It won't surprise you that there's a similarity in structure of these things. If, I'm going to say if if A equals e to the r, then we can say pt equals I'm sorry, I just did it again, didn't I? Kt equals k0 a to the t is exponential, and if a equals 1 plus r, then kt equals k0, a to the t is geometric. So how close are they? They're actually quite close. That's an empirical question. It turns out that how close are geometric and exponential growth models? And the answer is, if R is small, as it typically is for human populations, and the t, the time period, is short, then geometric and exponential are very close. If R is not small, for some species, the growth rate R can be quite high, or if T is very long, then they tend to diverge. At Berkeley, we go through a series of calculations and examples to determine how small R can be and how short or how long T can be before they tend to diverge. I may or I may not give you that problem later on, but for human populations, R tends to be small, and if we're looking at a few years, then the difference between the geometric and exponential models are quite small. So here's our bottom line. So if R is small and T is short, you can, that looks terrible, you can use whichever is easiest. And I think that's so important, I'm going to draw a box around that. So you can use whichever is easiest for you. Now, what we're going to do is in this class, we're going to flip back and forth. There will be times when it will be easier for us to do a geometric growth model. There will be times when it's easier for us to use the exponential growth model. And as long as I write things out and do it carefully, then you will see that it doesn't really matter. I can flip back and forth between the geometric and the exponential, and now you can see why that is, and we thank Jacob Bernoulli for that. I'm going to take a little break, and we'll come back in the next video.